Good afternoon. Today we're going to be looking into the Test 2 review set, and for what we have at the start. Okay, so we're looking at function values as well as domains of functions, and for what we have in the first part of the Test 2 review guide, and we have with the first problem, okay, we have a given radical function, okay, whereupon we have f of x is equal to the square root of x plus 11. And just for the portions we have here, for parts A and B, we're looking at the determination of function values. So again, we have f of x. Again, so this is a functional notation, again, for what we say is y. And that is set equal to the square root of x plus 11. And for part A, we're now looking at the y value whenever x is set to 25. And so for the y value, when x is set to 25, so y is going to be f of 25. And utilizing what we have for the radical function, so this will translate to the square root of 25 plus 11. And 25 plus 11 is 36, and 36 is a perfect square number, and so we have the f of 25 reduces to 6. For what we have in the case of part B, we're looking at f of negative 7. For the function value, we're looking at now the square root of negative 7 plus 11. And negative 7 plus 11 is 4. And the square root of 4 is 2. So again, we have ordered pairs such as 25, 6, and negative 7, 2. Those would be a couple of points that will be on the graph of y is equal to the square root of x plus 11. Now concerning the domain of f of x, again we have a radical function in the form of an even root, namely the square root. And since we have a square root, and because we're dealing with exclusively the real number system, we have the x plus 11 cannot be negative. Now it can be 0 and it can be positive. And if I write as an inequality statement in comparison to 0, so we have the x plus 11 is greater than or equal to 0, and solving for x, we're going to have the x is greater than or equal to negative 11, and this will be the inequality statement that defines what is allowed for x. And just looking at what we have, envisioning what is allowed among the values of x. Alright, so we have negative 11, and this value is included thanks to the equal sign. So if you were to graph, graphing is not mandatory, but if you were to graph, you would have a solid point on negative 11, and the rest of the values will be greater than. So we have a ray that's going to go to the right, and the upper limit will tend to infinity. So we have for the case in part C, we have for the domain of the function, again, what is allowed for x, so we have going from and including negative 11. So negative 11 is going to be in the bracket, and we have going unceasingly out toward infinity. Now, again, number one, we have f of x to be a radical function. Now, for what we have in the second problem, we have a blend of a rational and a radical function. And so we have for this item, again, we have given f of x is equal to x minus 3 all over the square root of x minus 4. And in this exercise portion, we're looking at outputs for a couple of specified inputs, and again, we're looking for the domain also for this function. And so just looking at what we have, and the first input value we're going to have at 5. So we have in part A, we have f of 5, and that is equal to 5 minus 3 all over the square root of 5 minus 4. And following through. Okay, so we have the difference at 2 in the numerator. In the denominator, have the square root of 1, and the square root of 1 is only 1. And 2 divided by 1 is equal to 2. Okay, so 5, 2 will be on the point on the graph of this particular function. For what we have in the case of part B, we have the input value x at 9. So with f of 9, we have 9 to take the place of x, so x minus 3 transforms to 9 minus 3, and for the square root of x minus 4, we're going to have the square root of 9 minus 4, and we have 9 minus 3 is 6, and we have over the square root of 5, and we have 6 over the square root of 5. This is one way that the answer can be displayed. And if this were an ALEKS exercise, I believe it would accept this version of the answer. But if there were any other way, like for 6 over the square root of 5, if I translated this without the radical in the denominator, I could just multiply by 1 in the form of the denominator divided by itself. And multiplying the numerators and denominators. We have 6 times the square root of 5. And we have in the denominator, we have the square root of 5 times itself, which will be the square root of 25, which will in turn reduce to 5. Again, 6 over the square root of 5 will suffice. And again, if there were any other way to express the exact form, you would have 6 times the square root of 5 all over 5. Now, for what we have in the case of the domain, again, with x minus 3 all over the square root of x minus 4, with x minus 4 we have a twofold restriction. Again, because we have, just like x plus 11 from the first problem, x minus 4 is inside a square root radical. So x minus 4 cannot be negative. And because x minus 4 is in the bottom part of the overall fraction, we have x minus 4 cannot be equal to 0. So x minus 4 cannot be negative, it cannot be 0, So this signifies that x minus 4 must be positive. So we're going to have here, as a comparison to 0 inequality, we're going to have the x minus 4 is greater than 0, and getting x by itself. Okay, so if I add 4 to both sides, we'll have the domain of this function to be defined by the inequality x is greater than 4. Okay, so 4 is not included since we have the exclusion of the equal sign, so you have an open circle. And for the defining graph, okay, this will be a ray to the right of that circle. And we have for this function expressing in interval terms. So we're going to have for the domain, okay, so we have starting past 4, so you have with an open parenthesis, we have 4, and going out to infinity and closed parenthesis. And so that would be the interval notation for what we have regarding the domain of the function described in problem number 2. Alright, now looking at what we have with the next set of items, okay, we're looking at parallel and perpendicular lines. And let me create just a little bit of room here. Okay, so we have item number 3. Okay, it says to determine the equation in slope-intercept form of the line with the following characteristics. And for what we have for item 3, okay, you're looking at a line that's going to run parallel to 2x plus y equals 4, and where that parallel line will run through the ordered pair 3, 3. Now to determine the parallel line, okay, first of all have to determine the slope value. And we have, in the case of the given line, again we have defined by the standard equation 2x plus y is equal to 4. And I have to find out what the slope is going to be. So if I rewrite what I have here in slope-intercept form, okay, so we're going to have that y is equal to negative 2x plus 4. Okay, so from y is equal to mx plus b, okay, the m value is going to be negative 2. And parallel lines are going to have the same slope. And looking for the slope-intercept equation for the parallel line. Okay, so the parallel line, so you have the slope at negative 2. And the point through which the parallel line passes is 3, 3. And we have enough information to go ahead and create the point slope equation pathway to finally determine the slope intercept equation. Okay. So with the point slope setup, okay, we have y minus y1 is equal to the slope m times the quantity of x minus x01. So filling in, okay, so y01 is at 3. So y minus 3. For the slope m, again we have negative 2. We have times the quantity of x minus, okay, and x01 is also at 3. So this is the point slope equation. and we have, and following through by distributing, we have negative 2 over the quantity of x minus 3. So this will be negative 2x plus 6. And getting y by itself, we have for the slope-intercept equation, this will be y is equal to negative 2x plus 9. So you got the slope at negative 2, and you can check out 3, 3. So the y value is at 3, and with x at 3, negative 2 times 3 is negative 6. Negative 6 plus 9 is equal to 3, and both sides of the equation equal. Now, for what we have in number 4, now we're looking for a perpendicular line, where we had the perpendicular line to be running as such with respect to the line defined by the equation 2x minus y is equal to 4, and where the perpendicular line is going to pass through 2, 7. So we have in this problem, so we have 2x minus y is equal to 4, and to determine the slope of this line, again I can refashion this and put in terms of the slope-intercept form. And just like the earlier given line, I'm going to move the 2x over, and we have negative y is equal to negative 2x plus 4. And if I follow through either multiplying or dividing the equation by negative 1, so you have the side values of everything to change. Okay, so you have negative y becomes positive y, negative 2x becomes 2x, and 4 becomes negative 4. So for this line, okay, we're going to have the slope is equal to 2. Now looking for the line that's going to run perpendicular and pass through 2, 7. Again, for perpendicular lines, okay, the slope values will have an opposite sign reciprocal relation. Okay, so for the given line, you have a positive 2. So for the perpendicular, I'm going from a positive to a negative, reciprocal of 2, which is 1/2. So the slope is equal to negative 1/2. And again, the product of the slopes of perpendicular lines will always be negative 1. And the point through which the perpendicular line passes will be 2, 7. And creating once again the slope to the slope intercept equation, we have the point slope pathway again. For y minus y01, so we have y minus 7. We have is equal to the slope m, which we have at negative 1/2. Times the quantity of x minus 2. So we have the point slope formula, and distributing to get closer to the slope intercept. So negative 1/2 times the quantity of x minus 2. And we have negative 1/2 of x, and negative 1/2 times negative 2 is going to be a plus 1. And we have, upon adding 7 to both ends, we're going to have that y is equal to negative 1/2 of x plus 8. And I can check, okay, so y is at 7, and with x at 2, negative 1/2 times 2 is negative 1, in turn negative 1 plus 8 is also at 7. Now, for what we have in the case of the next item, and we have with number 5, okay, we're looking at determining domains of functions, and just looking at what we have here. Okay, so you have a couple of functions whose domain we will be determining. Okay, so we have with both 5 and 6, okay, we have rational functions. And in the case of 5, okay, so you have f of x is equal to 2x plus 7 all over x squared plus 4x plus 3 okay, now we do not have any even root radical, okay, just a fraction. And for the restriction for this rational function, we have that the denominator, x squared plus 4x plus 3, cannot be equal to 0. So looking at what we have with this restriction, we're looking at determining the values of x that will be left out of the domain. Okay, so we have x squared plus 4x plus 3, and here we have a factorable trinomial, and the binomials that will multiply into it. We have x plus 3 and x plus 1, and neither of these factors can be 0. So we have for x plus 3, if this cannot be 0, well, we have the x cannot be negative 3. Now for x plus 1, the other factor, if this cannot be 0, well, we have the x cannot be equal to negative 1. So we have two specified values excluded from the domain. Again, negative 3 is left out, negative 1 is also left out, and in graphing you would have some representation of the exclusions of negative 3 and negative 1, and in this case open circles. But for everything else, we're going to have to be elements that will define the domain of the function, and we're going to have the breakdown composed of 3 sections, and we have at the lower end, okay, we have those values of x less than negative 3, and then we have with the line segment connecting the circles on negative 3 and negative 1, we have those values of x whereupon negative 3 is less than x is less than negative 1, and then we have at the remaining end, okay, we have for the highest end, okay, we have those values of x greater than negative 1, and we have the rest of the activity defined by increasing values in x. So we have for this function, okay, we have for the domain, okay, so we have from negative infinity approaching but not including negative 3, and we have bypassing negative 3. Again, we have parentheses around negative 3 and negative 1. And again, this is for the middle strip, and then we have for the remaining values, we have again those values of x which will be greater than negative 1. And now for what we have in the case of number 6, okay, we have another rational function. and in this one. Okay, so you have 2x minus 1 all over x squared minus 4 and looking at what we have here. Okay, so the nature of the restriction is the same. Again, the denominator cannot be 0 in value. So we have with x squared minus 4, we have a difference of squares. So factoring, we have x plus and x minus 2. And neither factor can be 0. So we have here, okay, so we have with x plus 2. That cannot be equal to 0, so we have negative 2 excluded. And with x minus 2 disallowed from equaling 0, we also have 2 to be excluded from the domain. And so just carrying out, okay, what we have here, okay, so I have negative 2, positive 2 left out. And again, you have 3 separate sections. So ray going to the left continuously, and ray going to the right continuously. And again, we have a line segment for the in-between values. So for what we have in the case of the domain, again, we have 2 exclusions from the domain, and so in interval notation, there will be 3 separate sections. Okay, so you have going from negative infinity, approaching but not including negative 2. Then we have bypassing negative 2. So you have parentheses around negative and positive 2. And we have for the rest, we have those values of x greater than 2. And the result here is the domain for what we have in the case of problem number 6. Now, for what we have in the case of number 7, we're sort of touching upon, again, similar exercises to what we had when we were working with the parallel and the perpendicular lines. Okay, and this time we're having to find out what the slope is going to be through a different pathway, and that will be from the slope formula. And we're looking at determining the slope as well as the slope-intercept equation of the line that runs through -1, -3, and 3, 5. And for this exercise, okay, so you have -1, -3. And 3, 5. Okay. And we don't have an equation from which we can attain the slope, so we just had to take the coordinates as they are and utilize the slope formula. So here we have y of 2 minus y of 1 all over x of 2 minus x of 1. And before we can use the slope formula, we want to go ahead and identify just what the x and the y values are. And I said it before, and I'll say it again. Just keep in mind, all ordered pairs are of the form x, y. And you could say the first order pair will be 3, 5, and -1, -3 the second. It'll still work, but since -1, -3 is given first, I'll have those numbers to represent x1, y2, and since 3, 5 is given subsequently, I have 3 to represent the second x and 5 the second y. So we have with these items to now utilize. For y2 minus y1, y2 we have at 5. We have subtracting, and y1 okay, we have at -3. And we have this difference all over that between x of 2 and x of 1. So x of 2 we have at 3. We got minus x of 1. X of 1 we have at -1. In both the numerator and denominator. Okay, so I have subtraction of negatives. And I can just change over to addition of the additive inverse. So you got 5 plus 3 is 8. And we got 3 plus 1 is 4. So the slope here is going to be 2. And setting up what we have and following through. Now you can choose either ordered pair to represent x1, y1 in the point slope backdrop. Okay, so you could choose either -1, -3. Or 3, 5. Again, we can choose either ordered pair and the point slope setup. And one might be inclined to say -1, -3 since that was the first introduced point. But let's say that if one is a bit hesitant about working with negative numbers and rather go with positive coordinates, they can do that as well. And so we'll go with this route. So we'll go with 3, 5. Okay. And so we have in the rewrite. Okay, so we have with y minus y of 1 is equal to the slope m times the quantity of x minus x of 1. Okay, so y minus y of 1. Okay, so your y of 1 is going to be at 5. So you have y minus 5 and equal to the slope m, which we just attained at 2, and times the quantity of x minus x of 1. So x of 1 is going to be at 3. And distributing 2 over the quantity of x minus 3. So we got 2x minus 6. And then getting y by itself. So if I add 5 to both ends, and it will follow. Then we had that y is equal to 2x minus 1. And you can test out this equation. So again, if y is at 5 whenever x is at 3, we want both sides of the equation to balance. Okay, so y is at 5, and with x at 3, 2 times 3 is 6. 6 minus 1 is 5. 5 is equal to 5. And it will also work out for -1, -3. So with y at -3, okay, the left hand side of the equation is at -3, and we want the right hand side to be as well. So with x at -1, we have 2 times -1 is -2. -2 minus 1 is also -3. And so that will check out. And so y equals 2x minus 1 is going to be, again, this slope-intercept equation, and again, the attained slope from earlier, okay, is at 2. Now, for what we have regarding item number 8, and this is going back to an individual function where we were looking at various inputs, and we're looking at what each output will be. Okay, and so we have, in the case of 8, all right, so we have the function f of x So we have at negative x squared minus x plus 4. Again, we're looking at f of 3. F of negative 2 as well as f of x plus 4. So for what we have here in the case of number 8, okay, so you have f of x equal to negative x squared minus x plus 4. And we have for the respective inputs, okay, so we have with x at 3, if I'm looking for the corresponding y values. Okay, so in the first case, right, so whenever we have x to be at 3, so f of 3, we're looking at taking the negative of the square of 3. Again, we have minus 3, followed by the addition of 4. Okay, so 3 squared is 9. Okay, so let me mention this. Okay, the negative of the square of 3 is not the same as taking the square of negative 3. Notice I don't have any parentheses around negative 3. So I'm taking the opposite sign of 3 squared. So 3 squared is 9. Opposite sign is going to be negative 9. Again, we have minus 3. Negative 9 minus 3 is negative 12. In turn, negative 12 plus 4 will be negative 8. For f of negative 2, again, we have what's going to be the negative of the square of negative 2. And we have minus negative 2. And we have followed by the addition of 4. Right. Now, again, negative 2 squared is 4. However, okay, the square of negative 2 is still affected by the negative sign at the front. So while the square of negative 2 is 4, the opposite sign of the square of negative 2, that is going to be negative 4. And minus negative 2, okay, so that's going to translate to the addition of 2. And we have plus 4. And you probably see that negative and positive 4 will cancel out. So f of negative 2 is going to be equal to positive 2. Now, for what we have in the case of f of x plus 4, okay, so instead of a numerical input, okay, we have a binomial expression, okay, in the variable x. Okay, so for f of x plus 4, okay, now we have the negative of the square of the input, so we'll be looking at the negative of the square of x plus 4 and minus the input, so we have minus all of x plus 4. So the minus is going to affect not only the x but also the 4. And I have plus 4 at the end. Okay, and let me just mention, okay, so we got the square of x plus 4. I'm just serving as a reminder. So for the square of x plus 4, so this will be x plus 4 times itself. And foiling out, okay, so you got x squared, and you got plus 4x, which will be 8x. And 4 times 4 is 16. All right, and so we have in following through, okay, so we got the negative, again, we have of x squared plus 8x plus 16, and distributing subtraction over x plus 4, so we're going to have negative x and negative 4. And at the end, okay, we have the addition of 4. And so you have constants at the end, so they can go ahead and cancel. And we have in following through, okay, so taking the opposite sign of the square of x plus 4, we're going to have negative x squared minus 8x minus 16. We have minus x to follow. And then combining like terms that we have first order in x. So we got negative x squared, and what's going to be negative 9x minus 16. So we have for the variable expression binomial input x plus 4. Okay, we have leading up to the trinomial output with negative x squared minus 9x minus 16. Okay, now crossing over to what we have in the case of piecewise defined functions. Oh, here we go. All right, so you have for number 9, okay, you have 3 sections here in terms of how f of x could be utilized, and how it is used is contingent upon the size of the input. Okay, and so we have f of x equal to 3 if x is less than 4, and we have the f of x is equal to the absolute value of x if 4 is less than or equal to x, which in turn is less than 8. And then we have the f of x is equal to 7 for values of x that will be 8 or greater. And so for what we have here, we're looking at determining, okay, the corresponding values of f of negative 4, f of 1/2, f of 6, as well as f of 15. And for what we have in the case of number 9, okay, so we have for f of x, and then we have equal to negative 3 if x is less than 4. And we have the f of x is equal to the absolute value of x if x fits within the compound inequality, whereupon we have that 4 is less than or equal to x, which in turn is less than 8. And we have the f of x is equal to 7 if x is greater than or equal to 8. Okay. And so we have for the first item, okay, so we're looking at f of negative 4. And we have next, okay, we have f of 1/2. And we have f of 6. As well as f of 15. In terms of what to do with each of these inputs, okay, we look to see which of the inequalities each of the inputs will belong to. Okay, so we have for negative 4, okay, so negative 4, okay, we have right off the bat, okay, negative 4 is less than 4. And because this fits inside, okay, the first inequality, well, the functional operative that corresponds, well, this comes out to just the constant value, negative 3. So any input size that is less than 4, the output is just going to be negative 3. And this will be ditto for 1/2. 1/2 is also less than 4. So the output again is going to be negative 3. And for what we have in the case of f of 6, okay, 6 is not less than 4, so we're not going to have f of 6 to be equal to -3. Now for the next, okay, 6, 4 is less than or equal to 6, 6 is less than 8. That statement is true. For 4 is less than 6 in the less than or equal to part, and 6 is definitely less than 8. So with 6 belonging in the second inequality description, we're going to take the second part of this piecewise defined function, where f of the input, in this case 6, is equal to the absolute value of the input. Here we have the absolute value of 6, which is going to be 6. And for 15 as the input, 15 is not less than 4, 15 is not between 4 and 8. However, 15 is greater than 8. So to say that 15 is greater than or equal to 8, that is true. So any input that is 8 or greater, okay, the output is just going to be the constant value of 7. So f of 15 is equal to 7. Now, for what we have with the other piecewise defined function, we have for number 10, okay, so you have f of x is equal to, and here instead of constants and an absolute value expression, we have two linear expressions in the variable x. So you've got f of x is equal to 4x minus 3 if x is less than 0, and we have f of x is equal to the quadratic expression x squared minus 1 if 0 is less than or equal to x, in turn is less than 5. And then we have at the upper end, we have that f of x is equal to 2x plus 1 if x is greater than or equal to 5. And looking at the determination of the following function values with the various inputs. Okay, so we have for this piecewise defined function, okay, so with f of x, we have 4x minus 3. If x is less than 0, then we have f of x is equal to x squared minus 1. If 0, again, is less than or equal to x, is less than 5. And we have the f of x is equal to 2x plus 1. If x is greater than or equal to 5. Okay. So we have with the input values. Okay, so for we've got f of -3. We have f of 0.6. We have f of 4.9. And we have closing out. Okay, so we're looking at f of 5. Okay. So for what we have here, okay, so you have f of -3. Okay, and any negative value is less than 0. So got -3 is less than 0. Now for 0.6, 0.6 lies between 0 and 5. I guess like 0.6, 4.9 is between 0 and 5. Now for 5, okay, that number appears at the end of the second inequality statement, and also we have it to appear in the last inequality. And so 0 is less than or equal to 5, it is less than 5, so that part is true. However, 5 cannot be less than itself. Okay, so the second statement is disqualified in terms of where 5 belongs, but with the last, now 5 is not greater than itself, but we do have it to be equal. So thanks to the equal sign appearing, okay, this last statement or inequality is going to apply. Okay. And in terms of how we go about following through, okay, so for f of -3, okay, we'll have the 4x minus 3 treatment. Okay, so here 4 times -3 minus 3, we'll have -12 minus 3, and -12 minus 3 becomes -15. And for f of 0.6, okay, again, this number is between 0 and 5, and so we take the x squared minus 1 portion, and with x at 0.6, so we got the square of this minus 1. 0.6 squared is going to be 0.36, and taking 1 away, so we have a negative difference in this case, whereupon we have minus 0.64. Now for f of 4.9, okay, again, that is also going to receive the square of the input minus 1 treatment. Okay, so you got 4.9 squared. Okay, so you have it 24.01, and taking 1 away, and the corresponding y value, okay, we're going to have it 23.01. And in the case of f of 5, okay, for any numerical input that is 5 or higher, okay, this will receive the 2x plus 1 treatment. Okay, so for this case, for x at 5, we have 2 times 5 plus 1. And we have 2 times 5 is 10, and we have plus 1, and 10 plus 1 is equal to 11. Okay, now for the next group, and we're looking at consolidating, in a sense, operations between functions as well as their domain. And for what we have for numbers 11 through 16, okay, we're working with a couple of linear functions, f of x and g of x. And I'm going to write these down. So we have the f of x is equal to 2x minus 12 and we have for g of x, now g of x is equal to x plus 14. Okay. And we're looking at the sum, difference, product, and quotient function results as well as their domain. And then we have next in line, we have the compositions, f composed of g of x and g composed of f of x and their respective domain. And just taking what we have with this pair. Okay, so we have f of x is equal to 2x minus 12, and g of x we have equal to x plus 14. Okay, and for what we have in the case of number 11, again we have f plus g of x and 12 we have f minus g of x. And we have also, okay, we have f times g of x. And again, the sum, difference, and product functions will have the exact same domain, and any restrictions will be limited to just combining the restrictions from f of x and g of x. So we have for f plus g of x, you're just going to be taking the sum of f of x and g of x. Okay, so we got 2x minus 12. We have g of x, which we have at x plus 14. And we have combining. Okay, so once I remove the parentheses, again I use the parentheses just to separate the f of x apart from the g of x. And putting together, okay, so got 2x plus x will make 3x. Negative 12 plus 14 comes out to 2. And so for the sum function, f plus g of x, okay, again, this translates to the sum of f of x and g of x. And so we have the output specifically at 3x plus 2. Now, for f minus g of x, again, we're looking at f of x minus g of x. Okay, so we have with f of x, we have 2x minus 12. And we'll have subtracting all of g of x. In this case, we have subtracting all of x plus 14. Okay, and removing parentheses. Okay, so 2x minus 12 is unaffected. But with x plus 14, with the subtraction before it, okay, we'll have the terms to become negative x and negative 14. And the difference, 2x minus x, we have an x. Negative 12 minus 14, okay, that would be minus 26. And for the product function, f times g of x, so we'll be looking at f of x times g of x. So f of x we have at 2x minus 12. And g of x we have x plus 14. And multiplying out, so we got 2x times x becomes 2x squared. And we have for the outside product, we got 2x times 14 is 28x. Inside product is going to be minus 12x, and joining together, okay, you got 28x minus 12x, so that will be 16x. And the last product, we have negative 12 times 14, so this will be a minus 168. Okay, and if I go ahead and identify the domain. Okay, first of all, with f of x and g of x, okay, both of these are linear functions, and you don't have any even root radical expression, nor do you have a fraction. And with the nature of f of x and g of x being linear functions, you can apply any 0, positive, or negative real value for x. And so we have for f of x, you have no restriction. G of x, you have no restriction, and that's going to carry over to the sum, difference, and product functions. And guess what? Any function or combination of functions that will end up having no restrictions, we have for the domain the set of all real numbers. Okay, so we'll have the sum, difference, and product functions to all have all real numbers for the domain. Again, that's for the reason that, okay, you can plug in anything for f of x, g, and g of x for these three operations. Okay, now for what we have in the case of the quotient function, again, we can have a domain that is distinct from that of the sum, difference, and product functions. And the reason for this is that, okay, now is with the g of x. Okay, so while we can have g of x, okay, to be any positive, negative, or 0 value in the sum, difference, and product functions, it is with the constraint that you cannot have a 0 denominator in a fraction that again, while g of x can be 0 in the sum difference and product functions, it cannot be 0 in the denominator. So for f over g of x, we have f of x over g of x, and for the functions, okay, we have 2x minus 12 all over x plus 14. And this result is already in simplest form. So just the mere substitution, got 2x minus 12 all over x plus 14. Okay. And here, okay, while the domain will be the set of all real numbers for numbers 11 through 13, we have an exception with number 14 because we have the constraint that x plus 14 cannot be equal to 0. Okay, and so in this case, if x plus 14 cannot be 0, okay, we have that x cannot be negative 14. And with negative 14 excluded, you're not going to have the set of all real numbers for the domain. Okay, and you'll have values of x around, but not including negative 14. Okay. So we have for the quotient function. Okay, so we have for the domain, instead of having all real numbers endlessly, okay, we're going to have instead those values of x less than negative 14. So you have parentheses around negative infinity and negative 14. And for the rest, the values of x greater than negative 14. So we have parentheses around negative 14 and infinity. And that would be the resulting domain for problem number 14. And again, so again, with the sum difference and product functions of the domain, you're looking at combining the restrictions for f of x and g of x. And in a sense, you're doing the same thing with the quotient function, but also the added possibility that there could be another restriction resulting from preventing g of x from being 0. And this is exactly what happened with 14. Now, for what we have in the case of the composition of functions, okay, now the domain is going to go by somewhat different requirements. Again, we have f of x equal to 2x minus 12, and g of x, okay, we have equal to x plus 14. And we have for the compositions. Okay, so we have for f composed with g of x. Okay. So we have f of g of x. Okay. And specify the input. So g of x is the input function. Which is going to be x plus 14. And for the follow through in terms of what to do with x plus 14, let the f of x definition be the guide. So f of the input is equal to 2 times the input minus 12. And with the input at x plus 14, so we'll have 2 times all of x plus 14 minus 12. And so we'll have 2x plus 28 minus 12. And for what we have for the result, so this will come out to 2x plus 16. So this will be the expression from composing what we have here in the statement f composed with g of x. Now for the domain, okay, again, you got the input at x plus 14. Again, you have a linear expression, and again, there's no restriction. And in case of the final output, you got 2x plus 16, no fraction, no even root radical. So you have no restriction. So input has no restriction, output has no restriction. So you have no restriction at all. So there's no real value that is going to be left out. So for the composition, whereupon we have f composed with g of x, the domain is going to be the set of all real numbers. And taking what we have in the case of number 16, okay, so you have, again, the other composition, we have the reverse of the order of the functions f and g. And for what we have in 16, okay, so you have g composed with f of x. So we have g of f of x. Okay. Now we have f of x is going to be the input function. So we have g of 2x minus 12. Again, so you have that input. Again, so you have just the linear statement, no fraction, no even root radical. So at this stage, x can be anything. So input has no restriction. And the follow through in terms of what to do with 2x minus 12, we go with what we have assigned for g to provide direction. Okay, so we have with the input plus 14. The input, we have 2x minus 12. And followed by the addition of 14. And so for what we have here, okay, so we're going to have 2x, and negative 12 plus 14 is going to result as a positive 2. So we have for this composition, we end up with 2x plus 2. And for this output, again, we have a linear statement, and there is no restriction. Input has no restriction, final output has no restriction. And okay, so we have this bit of history to repeat. So you have no restriction at all. So this bit of history repeats, and the domain, once again, we have the set of all real numbers. Now, for what we have in the case of number 17, okay, and we'll just look at parts A through D for these. And you're looking at just the domain. Okay, now we have a couple of functions, f of x and g of x. Okay. Now f of x, okay, we have this set equal to 3 over x minus 1. And for what we have in the case of g of x, for g of x, okay, g of x, we have x over x plus 12. Okay. And for what we have, again, for the following domains. Okay. Okay, so you have with f plus g of x, f minus g of x, and f times g of x. Again, these three operations will have the same domain, and just outlining the restrictions. Now for f of x, we got 3 over x minus 1. And again, the restriction is that the denominator cannot be 0. So x cannot be equal to 1. For x over x plus 12, which defines g of x, the restriction is that x plus 12 cannot be 0. So we have the x cannot be negative 12. And guess what? For the sum, difference, and product functions, okay, we had to work with f of x, so x cannot be 1. And also we had to be able to work with g of x, so x cannot be negative 12. Okay, so you have the same restrictions throughout these three operations. Okay. And so for what we're going to have here for the domain of these operations, you can just sort of envision, okay, like a number line. Again, so you have negative 12 and 1 excluded. So negative 12 is left out. 1 is left out. Okay, and so we're going to have, in the case of the activities, again, 2 exclusions, and we'll have, again, 3 sub-interval sections. So we have, for the domain, we have those values of x less than negative 12, and those values of x such that negative 12 is less than x is less than 1. And finally, we have those values of x which we have to be greater than 1. Okay, and we have finally, okay, so we have, in the case of the quotient function, we can have a distinct domain, and in this one case, we have for f over g of x. Okay, we still had to be able to work with f of x, so x cannot be 1, and with g of x, okay, so we have that x cannot be negative 12. And for what we have in the case of f over g of x, okay, so you have f of x over g of x, and f of x, okay, so you have 3 over x minus 1. G of x, we have a x over x plus 12. So right now we have 3 over x minus 1. divided by x over x plus 12. And again, if I divide by a fraction, it'll be the same as multiplying by the fraction's reciprocal. So you have 3 over x minus 1 times what's going to be x plus 12 over x. And guess what? We have in the role reversal. Okay, so x plus 12 was on the bottom, now it's at the top, and x is in the reverse situation. So, and just leaving in the factored form, so you have 3 times, okay, the quantity of x plus 12, and this time we have over the new denominator x, and we have times the quantity of x minus 1. And so with x now situated in the denominator position, okay, x cannot be 0, so this is going to be our new restriction. And what separates the domain of the quotient function apart from the others, and I won't draw the graph on this one, but just to envision, so you're still looking at values of x less than negative 12, and the next smallest value is going to be 0 this time around. Okay, so you have values of x between negative 12 and 0, but not including negative 12 or 0. And then we have values of x between 0 and 1. And then heading down the home stretch, okay, we have those values of x which will be greater than 1. Okay, so with the added restriction that x cannot be 0, okay, we have 4 sub intervals as opposed to 3, which we have for the sum, difference, and product functions.